So, what do you think about the conservation of momentum in space? It turns out that this is a universal law, just like really everything we're studying right now. It's not just stuff that applies here on Earth. I can't wait because we're going to be studying gravity pretty soon, and that's one of my favorite topics. So I have here on the screen an example of a Newton's cradle. I'd show you my real one, but if you know Bryce, the senior, he broke it last year, and I haven't replaced it yet. So we're going to go with virtual because honestly, we're doing online school anyway. So you've probably seen one of these before. It's a series of however many balls hung by strings that are the exact same length. That's very important that they're the same length because it works differently. The physics and the rhythms you see work differently if you have different length strings. And with the Newton's cradle, you've probably played with them before. You lift one up and you see the motion of the red one I lifted up, and this purple one is going up to the same height that I lifted the red one up to originally. Actually, it looks like this one does have some dampening in it, so it's going not quite as high, but pretty close to. Now, what I want to see here is what happens if I lift two balls. Have you ever done this before? I think most of you have probably played with a Newton's cradle before. The conservation of momentum said that when I lifted one mass up, it was going to displace one mass on the other side. If I do two masses and give them twice as much mass if they were stuck together, and then they're going to have a certain speed as they fall, what's going to happen when the other side, when it hits the other side? So you probably already have made a prediction. Here we go. All right, is that what you predicted? I lift two, and I have two fly away. What happens if I lift three? Now there's only two left on the other side. What do you think is going to happen? Maybe you've played with this one before. On your mark, get set, go. We lift three, we see three move on the other side. If I were to do four, I see four swing to the other side. What's great about these, now this only works because these balls are all the exact same mass and they have the same length of string. And of course, if I wanted to be really boring about it, I could lift five, but they just swing. Anyway, I've put a link to this Newton's cradle in your lesson page, so if you'd like to play with it, you are welcome to. But let's talk for a moment about the conservation of momentum and mathematically what that means. So I like personally to compare this to another conservation law you've learned before. So keep in mind, this is from chemistry. In chemistry, I expect that you were taught the conservation of matter. And that was the idea that matter can neither be created or destroyed. If you were to burn a piece of wood, you might feel like there's less matter because the ash looks like there's less. But realistically, if you look at the air, the water vapor that escapes, the particulates that change to smoke, all of these, if you collected all of that matter, it would equal the same amount of matter you had in the beginning of the process. Conservation of momentum is going to be a very similar idea. With conservation of momentum, I hope you saw this in your homework from last time. What we see is the total, put a period there, momentum before a collision or explosion equals the total momentum after. Mathematically, we can take this, and it's usually easier to describe things in terms of their equations. Mathematically, what we say is the sum of our momentums initially equals the sum of our momentums finally. So I'm going to have you do 3 examples, and I'm going to go through and show you how some of these will work. If I can find my mouse on my screen. There we go. Okay, so I'm going to have you do some carts that are going to collide and they're going to explode. And I'm going to describe to you what's going on with each of these. So, you see down here at the bottom, you have 3 options. We're going to have an elastic collision, inelastic, and explosion. And I'm going to go through and I'm going to describe each of those 3 to you and what makes each of them unique. Remember these terms, especially elastic collision and inelastic collision, because they're going to come back again in our next unit when we study energy. So what we have here is, you can't really tell very easily because of the way these graphics work, but we have a spring here and another spring here. And this is set to do an elastic collision. Really quickly over here. Elastic collisions bounce off each other. That's as simple as it is. The objects bounce off one another. So, as I set this back up again, you can adjust the initial velocity however you'd like. I want you to notice some are positive, some are negative. I'm going to talk about those with the math in a minute. You can adjust the mass if you would like. And you can even pick up the cart and move it wherever you'd like. Whenever you're ready, you're going to hit start. And you're going to see what happens. Notice here we have a negative velocity and we have a positive velocity. So, what do the negatives mean? Do you see with the direction on each of these? Both at the beginning for the blue and at the end for the red. That those negatives indicate the direction. If you're moving to the left, you have a negative velocity. If you're moving to the right, you have a positive velocity. And what happens is, we can see our red car gives much of its momentum, not all of it, but it gives much of its momentum to that blue car. And that blue car ends up moving backwards very fast because the red car was twice as massive, plus it was moving much faster, which imparted more momentum to the other car as they bounced off each other. Let's do inelastic next. And let me show you here where it's going to be hard to see. Do you see here that spring changed to something else when I changed it to an inelastic collision? With the inelastic collision, what they've done is they've put magnets on this. And so what happens when you have 2 magnets? Well, it depends on if they're what direction your poles are faced. We'll talk magnets perhaps a little bit later in the year, although that's a topic that we don't always get to. So with our magnets, they do have these faced, so they're going to want to stick together. So I'm just going to leave my initial constraints the same here. But I hit start and they stick together. This is an example of an inelastic collision. Now, it's not the only way you can have an inelastic collision, but it's the only way we're going to talk about for this unit. Anytime you have objects stick together, we're going to call that an inelastic collision. So I'll add that to our notes. Objects stick together. All right, and our last one, the collision. The collision is going to be, or sorry, not the collision, the explosion. Now notice here, instead of having our magnets, our carts are right next to each other. It's not going to let me move them at all. They're not moving. I could set them to move, but whatever I do, it's going to do the same thing for the red and for the blue. Because the idea with the explosion is they're stuck together, and this is a little stick of TNT, stick of dynamite here. And what's going to happen is we're going to have an explosion that's going to take this one object that's 3 kilograms, because we've got 2 kilograms on the red, 1 kilogram on the blue, and they're stuck together, so we treat them like one object. This is going to explode the 2 pieces apart, and we're going to look and see what happens to each of these pieces. Kabam! There they go. And we can see that the lighter car moves faster than the heavier car. And because I had given them that initial speed, they are moving slightly. Let's start with just a velocity of 0. So they're not moving, and then they explode apart. Okay. So, to finish up that part of our notes, our explosions we'll say push apart 2 objects that were stuck together. Now, we could talk about more impressive explosions, like Mythbusters. If you've ever seen them do their explosions, they were known for it when they were on TV. I had a professor that he actually had a show on Discovery Channel years ago that it was all about exploding buildings. It was really cool to watch. It was just a short-lived show, though. Those sort of explosions we'll talk maybe a little bit more about, but mathematically, because there's so many pieces involved in one of those explosions, you're not going to want to do the math on it. And what I want to focus on right now is the math of how this works. So, coming back to our equation up here. Sum of the momentums before equals the sum of the momentums after. Let's do an example. And I'm just going to pick a random one. Let's do an elastic collision. Let's say that my first cart, let's say it wasn't moving, but I'm going to move it this way. And let's say my blue cart is moving at 4 meters per second, and I'm going to keep the masses the same. So, let me rearrange my windows just slightly. Oh, went onto the wrong screen there. How are your study groups going, by the way? I hope they're going well. You guys, I've been really impressed with a lot of you and how you've been doing with your study groups. Okay. So we have that. And what I want to do is I want to get down my initial information so that I can start setting up my equation here. So let's do this as an example. We have an elastic collision. I'm going to draw my picture. Initially, I have, let's even color code this. We have our red car, and we have our blue car. And I didn't move it quite far enough to be able to see. Let's see, I made the red car have a mass of 2 and an initial velocity of 0. So, my mass of my red car initially, well, actually the mass isn't going to change, so I'm not going to worry about the initial, but it was 2 kilograms, but my velocity does change. The velocity of the red car initially is going to be 0 meters per second. On the blue car, I gave the mass of the blue car 1 kilogram, and I said that the initial velocity of the blue car was -4 meters per second. I can make predictions about what's going to happen finally if I know some of the constraints. But let's go through and prove to you that these will be the same first of all. If I wanted to find the sum of the momentums initially, that means that I'm going to take the momentum initially of the red car, and I'm going to add to it the momentum initially of the blue car, which again is just mass times velocity. I told you back when we were studying our 2D forces especially that was as bad as the math is going to get. The math is going to be pretty easy for the rest of the year with these equations. So we have here the mass of the red car times the velocity of the red car initially, and then we're going to add to that the mass of the blue car times the velocity of the blue car initially, which will give us 2 times 0 plus 1 times -4, which comes down to equal just a straight up -4. Now let's look and see what happens finally. And we should get -4 out of that situation as well. So I'm going to go ahead and get my cars ready. I know that my masses are not going to change, so I'm going to go ahead and write those. If for whatever reason the mass did change, you would still have this law work. But we're just not in this situation going to deal with masses changing except for when they stick together or they started together. I'll show you how that works when I do an example of those. Okay, so let's start and let's see what happens to our velocities, especially after the collision. It's going nice and slow because I didn't set it too fast and I kind of had it far away. Okay, there we go. So they collide off each other. One bounces back at -2.7 and the other at 1.3. So we'll write those down. Our velocity final of the red car was -2.7 meters per second. The velocity final of the blue car was 1.3 meters per second. And if I go through and find the sum of my momentums finally, I'm going to get the momentum of the red car finally plus the momentum of my blue car finally in the final position. I should add here some arrows too. I should have added arrows up here as well to show how that was working. Okay, so the mass of the red car, let's make that a subscript, times the velocity final of the red car plus the mass of the blue car times the velocity final of the blue car. Of course, I expect you'll probably go faster than I am, but this is the first example I've done for you, so I don't want to do anything that would lose you. I know when I was a student, I'd have my professor, my favorite professor, he would always do an example in class and he'd skip steps. And then he'd always say, and it's obvious that this is the answer. And we would just stare at him like he was crazy and we'd go, that is not obvious at all, because we didn't see all of his steps since he had done some in his head or had done some before class. All right, so let's see, we've got 2 times -2.7. And then I'm going to put parentheses around all of that. And then we're going to add to that 1 times 1.3. And there we go. Now, of course, it's not exactly the same here, but blame that on how many decimals they gave us in the problem. Don't blame that on the law of conservation of momentum. So let me show you here. So this would be kilogram meters per second. Forgot to put that on the previous one. Kilogram meters per second. Okay, so these are slightly off from each other, but realistically, the fault here lies in the interactive itself. They should have given us more decimals here and here. And because they didn't, things rounded off differently. Let's do an example where I will expect, let's see. If I do this, I should have a more perfect collision. So I have -4 here. They're the same mass, and it imparts all of its momentum here. So we start with -4 times 1 as our initial momentum of the blue car, and it transfers all its momentum to the red car. Once you start getting into some of these different masses and ratios, it might be a little bit off, but so long as it's within 0.1, treat it like it's the same number. Because again, it's the fault of the program, not the fault of the law. Okay, so that's how the math works. What you're going to do for your homework is you are going to verify that this really does work. So let me show you one that looks like, or let me show you what this homework looks like here. Now the program I'm using, I can't draw on the screen here, but I want you to remember, I will put it here on the notes. We'll go like this. Okay, so I want you to see where it has your chart and it says delta momentum. There are a couple things here that I just want to remind you of, otherwise you're probably going to make some mistakes on this worksheet. Anytime you see change in momentum, that's going to be your momentum final minus your momentum initial. Everything that's a change in is always final minus initial. And remember, P stands for momentum because M already stood for mass. All right. So, where it says red cart, and I apologize, this would be easier if I could draw on the screen. I just can't with this browser. And it's going to say there's going to be before and then after. And you have those lines that you're going to fill in. Kilograms times meters per second equals here, kilogram meters per second. Super sloppy, sorry about that. And then blank kilograms times blank meters per second. Oops, sorry. Meters per second equals blank kilogram times meters per second. This right here is your momentum initial of the red car, and this right here is your momentum final. So make sure you're taking momentum final minus momentum initial to find your change in momentum. When it asks you for your system total, right here, you're going to add together the momentum of the red car before and the momentum of the blue cart before to find that system total before. And keep in mind, you're going to get some negative numbers every once in a while because your velocity sometimes will be negative. That you need that. That's on purpose. And you could have negative numbers show up anywhere here. Momentum is a vector quantity, which means direction matters. And we show direction, remember, in physics with negative numbers. So let's do one that's going to include some negative numbers, and then I'm going to leave you to finish the work on your own. Let's do and I'm just making up my own examples here, by the way. I'm not necessarily doing ones that show up on your worksheet. Oh, apologies for the technical difficulties. There we go, that's what I'm looking for. I wanted to be able to scroll. Okay. Let's do an inelastic collision. Let's set them both to the same mass. And let's see. I want everything to go in the negative direction. I'm going to up that to 5, but other than that, that's not going to matter. Let's give this a little velocity too. Let's have them collide, and I'm going to change that to 4. Okay, so remember, in physics, you always start by drawing the picture. So I'm not going to put as much time into my detail as I did in the last one, because this is the second problem I'm doing for you. But I'm going to do an inelastic collision. And I'm going to draw my picture. Let's see, I'm going to do a initial picture, and I'm going to do a final picture. I'm going to do the two of these together just because I'm color coding. That way I don't have to jump back and forth quite as much. So the mass of my red cart is 2 kilograms. The mass of my red cart is still 2 kilograms. And my initial velocity was a positive 2 meters per second, velocity of the red car. My velocity of the red car finally is something to be determined. And then on my blue cart, I'm using a mass of the blue cart to also be 2 kilograms. Now this one's inelastic, so they are going to stick together. And we are going to have the mass of the blue cart still equal that 2 kilograms. And while I don't know what my final velocity will be yet, I can tell you it'll equal the mass of the red cart because they're stuck together. You can't have one going faster than the other if they're stuck together. Alright, but initially I set it to go -4 meters per second. And then let's show I'm going to have this one going this way and this one going this way. Now, I bet you can predict what direction these both will travel because I did set them so they were the same size, same mass. And you can see one of them's got a bigger velocity, which means it's going to have a bigger momentum. So even before I start the problem, I'm going to guess my whole system will go this way. Just because this one has to have a bigger momentum because the masses were the same, but the velocities were different. So therefore the bigger velocity gives me more momentum. All right, so let's see how this one works. Let's go ahead and hit start. They slowly come together and bam, and then they're going at -1 meters per second off to the side here. So we've got -1 meter per second here, -1 meter per second here. Oops, put my fraction in the wrong place. So what happens when you don't get enough sleep? You guys saw my son in the last video, and isn't he super cute? You're going to get to meet him very soon during synchronous class, because that is going to be coming up soon. I'll let you know exactly when by the end of this week. I am trying to make some decisions for myself before I commit. Okay, so we know that the sum of the momentum before equals the sum of the momentum after. And so what we have here, and I'm going to show you, this is, I'm maybe going to do the math a little different than you would have done, maybe the same, we'll see. Initially, I think you guys will probably do things the same way that I would do them. We have two different items, so I'm going to take the mass of the red car times the mass initially of the red car plus the mass of the blue car times the initial velocity of the blue car. And I'm going to compare them. So this whole thing right here, I didn't color code it this time, but this is your initial here and here, your initial momentums. Your final momentum, because these are the same mass, I'm going to go ahead and just call this my big mass is 4 kilograms. Okay? That is completely a legal move. It sounded like I said illegal. It is a legal move. There we go. And this is going to be just the total final velocity because they're going the same. It is 100% legal to put them together and treat them as one large mass. So mathematically, let's see if they really are the same. If I plug in my numbers, I have 2 times 2 plus 2 times -4, and I want to see if that is equal to 4 kilograms because I have 2 kilograms and 2 kilograms stuck together makes a total of 4. And, oops, not -4, but -1 is my velocity. So I have here 4 plus a -8 equals -4. And voila, I see that these two do equal each other. In other words, yes, momentum is conserved. Now, next week, we are going to do a little more work on this idea of conservation of momentum. Today's examples are just going to be about proving that it's true with these interactives. Keep in mind, you also should be working on your car safety features. I know you, and I know you're procrastinating, so I know you have forgotten about it, but you should be working on your car safety feature presentations because those are going to be presented and they're going to be worth a test grade. My goal is by the end of next week, they're due. Okay? So, and if it's not by the end of next week, it will be very early in the week thereafter. So, that is where we stand today. Your assignment should be super easy today. I am starting to catch up on my emails. Some of you did hear from me. If you need me, I'm still not being super faithful about checking my email all the time, but my goal is to try to check it at least every 2 days. And then once I come back, it will be every day at that point. My goal, and don't hold me to this, but my goal is actually to be back on Tuesday. Like, what is that? A week from the day I'm making this video. The first day of the quarter. I might push that off by a week, but we'll see. I'm not getting a whole lot of sleep at night because my son gets up a lot during the night, but that is my goal. And so I'm going to decide tomorrow or on Thursday. I'm going to decide before the end of the week if I really think I'm up to being able to be present to teach you, if I'm really going to be any good for you. But if I'm not going to be ready by this week, I definitely will be ready by the next week. So you will see me again soon. Sorry. Anyway, I hope you're doing well. Yeah, if you need anything here with the end of the quarter, you can go ahead and email me. Caitlin also is sending me anything you email her that she can't take care of herself. So between the two of us, we should take care of you. Anyway, we'll see you later.